Welcome back. Let's talk about rocks. So we'll take a series of videos now to introduce rocks since we've talked about minerals. Reminder, rocks, for the most part, are kind of defined as an aggregate of two or more minerals, usually. Sometimes rocks can be made of one mineral, sometimes it can be made of non-mineral matter like organic material, but in general, that's what a rock is, usually two or more minerals kind of combined. So let's talk about first igneous rocks. These are all examples of igneous rocks. I'll tell you kind of what we're looking for, what we're seeing here, but just kind of train your eyes when you see things like holes, air holes, or different crystals kind of all merged together, that those are probably igneous rocks. So we have the rock cycle. The rock cycle kind of defines how one rock can change to another rock type. There's igneous rocks, there's sedimentary rocks, and then there's metamorphic rocks. It doesn't have to go in a circle. It can go any which way. There's a number of processes involved, but for this section, we'll focus on igneous rocks. Now, the reason we usually start talking about igneous rocks when we first introduce rocks is because, remember, when Earth first formed, it looked like this. Right? A hot molten ball of hot magma and lava. And what an igneous rock is defined as is a rock that formed from cooled magma or lava. So early Earth looked like this. When it began to calm down and cool down after all the asteroids and meteoroids eventually hit and things started to cool down, igneous rocks were the first rocks to form, because it's cooled magma or lava. So this section we're going to focus on just this portion of the rock cycle. So talking about magma, if magma cools below ground, that's known as an intrusive igneous rock. If magma makes its way onto or close to the surface and cools as lava, then that is known as an extrusive igneous rock. So all igneous rocks cool and crystallize essentially from magma, or they solidify from lava, which are actually two different things, or they are consolidated from pyroclastic material. More on that momentarily. So magma is the term we use for any molten rock, any molten material below the surface, any liquid rock that's so hot, any rock that's so hot it turned to liquid. If that's below the surface, we call it magma. That very same stuff, when it reaches the surface, is called lava. It's kind of like two different names for the same exact stuff. Molten rock below ground is magma. Molten rock at the surface is lava. But also, and so this is all tied to volcanic activity. And in volcanic activity, oftentimes stuff is exploded out. That's not lava. And so pyroclastic materials are produced and ejected by that explosive volcanic eruption. Here's a nice little diagram kind of illustrating a volcano. We're not going to necessarily get into too much how volcanoes work in this class. That's Geology 101 or Geology 110. But for the sake of knowing where rocks come from, we touch on it very briefly. So again, magma is molten rock below ground. Hot molten rock, hot liquid rock below ground. Lava is that very same stuff. So magma, and as soon as it gets to the surface, that very same stuff is lava. Two different names for kind of the same thing, just depending on where it's at. So magma below ground, lava above ground, and pyroclastic material is any stuff that gets exploded out. Ash or any number of rock materials that gets exploded out of a volcano. Excuse me. So there are different categories of igneous rocks. There are extrusive igneous rocks, extrusive, to extrude, to exit. These formed on the surface, so they formed from cooled lava or pyroclastic material. And we also have intrusive igneous rocks that form on the inside. Sometimes they're known as plutonic rocks. These formed from magma in the crust, and we refer to large bodies of cooled magma that form rock as plutons. So here's a chart that shows a number of different structures. So these some plutonic igneous rock structures. We have large Batholiths are large intrusions of cooled magma. Smaller intrusions of cooled magma are called stocks. If it's a mushroom shaped, it's called a laccolith. We also have vertical dikes and horizontal sills. So if magma kind of intrudes vertically into cracks and rocks and cools, it's known as a dike. If somehow magma goes horizontally, sometimes through rock layers or in between rock layers, it's known as a sill. So those are intrusive bodies. Here's just another kind of look at the same thing, but I like to show this one because it shows the 3D nature of dikes and sills. They're not just like tubes that go up or sideways. They're these planar features. So, in any case, if we're trying to identify a rock as igneous, which then would indicate that, oh, this rock was formed via a volcanic process or an intrusive plutonic process, so we can start to put together the historical geology of an area, we have to look at the textures of an igneous rock. Textures are the size, shape, and arrangements of crystals, grains, and other constituents of a rock. Igneous rocks have several textures that relate mostly to the cooling rate of the magma or lava, as well as some other characteristics of the magma or lava itself. And these characteristics include, and I'll just read them off because we'll define them here, aphanitic, phaneritic, porphyritic, pyroclastic, vesicular, and glassy. When we're looking at aphanitic igneous rocks, or pyroclastic, or vesicular, or even glassy, we're looking at extrusive igneous rocks. When we're looking at phaneritic igneous rocks, we're looking at intrusive igneous rocks. They cooled on the inside. Porphyritic is kind of a mix of both. So let's talk about all of these, shall we? So igneous rocks undergo a process called crystallization, where the molten rock made up of molten mineral grains begins to form and grow in the cooling of magma and lava. And the rate at which the molten material cools determines the texture of the igneous rock. So lava on the surface cools very fast, right? The surface of the earth is much cooler than inside the earth. So when lava cools on the surface, it does so relatively fast. So that affects the size of the minerals that can grow as it's cooling. When magma, which is molten rock below ground, kind of cools, it's much hotter below ground, so it takes longer for it to cool. In that process, for it to take longer to cool, bigger mineral crystals can grow. Because it takes a long time for that material to cool down. So rapid cooling gives us small crystals in igneous rocks. Slow cooling gives us large crystals in igneous rocks. Here's a little bit of visual of what that kind of might look like. So as lava cools very quickly, the minerals don't have time to grow and combine and kind of expand amongst one another. So you get igneous rocks that you can't really pick out different mineral grains. Remember, rocks are 2 or more minerals, but I'm having a hard time picking out different minerals. It just all looks black to me. Whereas magma that maybe cooled slowly, the minerals had time to bunch together, to grow a little bit, so the mineral grains grew much bigger. And in intrusive igneous rocks, I can pick out the different colors. I see black, I see white, I see a little bit of yellowish, orangish stuff. So that lets me know this rock actually cooled below ground, because it cooled slowly, where I can now visibly see these different mineral grains. I can visibly pick out the different colors. Here I cannot. So, let's talk about aphanitic texture. Kind of some Latin roots in there. So a meaning not, phaner meaning visible. So these are igneous rocks that have a texture where I cannot see with my naked eye the crystal grains. They're there and I can see them microscopically, but with my naked eye it's not visible. These are volcanic in nature, or extrusive. They cooled very slowly. They cooled very rapidly on the Earth's surface, so they only formed very small crystals that I can't see with my naked eye. Under a microscope I could, but this is just more so with your naked eye. So you need some sort of magnification, so it's not distinguishable, not visible crystals with the naked eye. And again, these are extrusive igneous rocks, and some names that are some common extrusive igneous rocks include basalt, andesite, and rhyolite. Looking at this image here. So we have a volcano, and lava is cooling on the surface. It's cooling very quickly, and it can form, for example, basalt or rhyolite. Really, you can't really pick out the different mineral grains. Maybe a little bit, but for the most part you can't, unlike here where you can kind of see those. So more on those here in just a second. So this would be aphanitic. I can't really see and pick out the different mineral grains here. Under a microscope I could see it quite clearly, but kind of with my naked eye, not necessarily. The kind of opposite of aphanitic textured igneous rocks are phaneritic igneous rocks. Phaner meaning just visible, so I can visibly see the different mineral grains, the different crystal mineral grains. These are plutonic or intrusive igneous rocks. That word plutonic or pluton comes from the word the god. I don't know if it's Greek or Italian. I don't know. Someone help me out with that. I guess the internet could. But it's either the Greek or Roman god Pluto, and Pluto is the god of the underworld, below ground. So hence plutonic, underground. So these are plutonic igneous rocks. They form from cooled magma inside the ground. They crystallize and cool very slowly, so they can grow larger visible crystal grains that you can pick out with your eye. They're not gigantic necessarily, but you can at least pick up a rock and pick out and see the different colors with your naked eye. And some examples, just names of intrusive igneous rocks, include things like gabbro, diorite, and granite. So if we're getting cooled magma below ground, we're looking here, things like, again, gabbro and granite. Now, what's interesting to note, again, because magma and lava, just the same kind of stuff, just depends on where it cools, right? We can get igneous rocks that chemically are the same exact stuff. Because again, maybe it's magma below ground and it's lava above ground. Maybe some of it cooled below ground, some of it extruded to the surface. So now I get a very rapidly cooled igneous rock with small crystal grains I can't see with my naked eye. And now I get a larger grained igneous rocks with different minerals I can pick out, visible crystals I can pick out. So chemically, they're the exact same thing. Chemically, they're made of the exact same stuff, but they just cool differently, so they have a different texture. For example, looking at granite and rhyolite. Chemically, pretty much the same exact thing, right? Chemically, if I looked at the minerals that they're made out of, they're made up of the same minerals, giving it the same chemical composition. However, one just cooled below ground, so I can now pick out the different colors. I see some clear and some white and some pink and some black. So magma cooled below ground, giving this igneous rock a phaneritic texture. But that very same material, if it made its way to the surface and cooled on the surface, cooled very quickly, these crystal grains I can't see. They're too small. Under a microscope, I might be able to pick it out, but I can't with my naked eye. So it's chemically, these two rocks, granite and rhyolite, can chemically and mineralogically be the exact same thing. It's just different textures depending on where it cooled. So rocks tell a story. All right, this is your first introduction that rocks tell a story. Minerals, some minerals are associated with other earth processes, but rocks really do tell a story. And starting with igneous rocks, they can tell a story of volcanics, of a volcanic area. It can tell of a story of tectonic uplift and boundaries, because if granite cooled below ground, but yet here I'm walking in mountains made of granite, but granite cooled below ground. How the hell am I walking on a mountain that's made of granite? Well, tectonic activity must have uplifted, and maybe convergent boundaries pushed things up, or any number of things. So you can start to tell a story of an area based off just really one little rock. So anyway, we're going to pause here. When we come back, we're going to continue this section on igneous rocks. We'll talk about more rock textures, as well as a few other items on igneous rocks, and we should have one more video to round out this section. See you back here in just a second.